Hello, welcome. Another botanical garden day, beautiful outside. There are two handouts today. One of them is another set of lecture notes, and the other is the second programming assignment. With respect to the second programming assignment, there's going to be a review session tomorrow, 11 o'clock upstairs on channel E1, that will talk more about Verilog, and in particular more parts of Verilog and the programming assignment and things you need to know for the programming assignment. Careful here, it looks like we've got two piles of the same thing. Take a look at that. There's homework due next Thursday, homework number 3. But because that's the last day before the midterm, the Tuesday after that, we're not going to allow any lates on the third homework. Now, we've also had a week and a half for it, so that shouldn't be much of a problem. But what we'd like to do is to distribute the solutions to homework 3 on the same day that you turn it in. So no lates for homework number 3 next Thursday. The midterm is still on schedule. We're having the midterm on St. Valentine's Day, unfortunately. Tuesday the 14th. It will be in the evening, 7 to 9 p.m. It will be in Terman Auditorium, and the SITN students need to come in. There'll be no lecture on that day, so you don't have to put up with 282 twice in one day. But you need to come in. Tuesday, February 14th, 7 to 9 p.m. for the midterm in Terman Auditorium. I'll say that several more times so you get a chance not to forget it. There will also be a midterm review on the Friday before that, on February 10th. And in fact, that midterm review will be a double length, and I think it's going to be from 10 to 12 instead of 11 to 12. Same place, same TV channel upstairs. That's Friday, February 10th. Any questions about that or other administrative items before we go on? We've been doing pipelining, and let's just recap where we are. We were enthralled by the idea, which theory told us that we could speed up our implementation of a RISC-like processor by a factor of 5, simply by taking the hardware we already have and dividing it into stages and having 5 instructions executing simultaneously, minus some overhead for latches and quantization effects when we try to make all of the pipeline stages equal size. But then we began to get into the details and realize that, well, it isn't quite all as advertised, and things are going to slow down a bit, and we found at least 3 different ways in which things will slow down. One of them are structural hazards, where there's something in the hardware that an instruction may need at more than one stage in its execution. Well, we got around that easily for DLX by simply designing the pipeline and designing the instruction set so that there aren't any structural hazards, that each resource is used only once in the execution of an instruction, and all 5 instructions can be executing together. The other issue which keeps coming up is branches. Branches have been broken in all of the sort of example pipelines I've shown you so far, and we have yet to deal with that problem, and hopefully by the end of this class we will have dealt with that problem and we'll get branches to work correctly. Then the third class of problems are the data hazards, instructions that use or modify results that previous or future instructions may need. And there were 3 kinds of those. There were the sort of true data dependencies, the read after write hazards, where one instruction writes a register and some following instruction, let's say the next instruction, uses it. And our pipeline would not normally allow that to work right. And we'll go over today how we can fix the pipeline to do that. The other 2 classes of data hazards, the write after write and write after read dependencies, I think I convinced you, in fact, are not a problem for us now. At least for the integer DLX pipeline, those are not hazards that cause any incorrect execution. We'll see later as we elaborate the DLX pipeline for floating point operations and look at other pipelines that in fact read after write and write after write hazards are a significant issue, and we'll need to do something about them, put hardware into the machine to fix them. I was trying to think of what to bring in as a hardware historical artifact related to pipelining, and in fact I couldn't find one, so what I brought in instead is a book. This is about 30 years old and I think long since out of print. It's a book that describes the machine which probably was the first pipeline processor. It was an IBM processor called Stretch, also known as the 7030, which they began to design in about 1954, and in fact wasn't completed and delivered to its first customer, which I think was Lawrence Livermore Labs over here in the East Bay, until 61 or something like that. So it's a machine that had a very long gestation period. And in fact, it was a machine that on the whole wasn't a great commercial success. They did eventually get it to work, and they built, I think, a dozen of them or something like that. But by the time it came out, there were other competing machines, even from IBM, that turned out to be much more commercial successes. But it was a machine, in fact, that had very aggressive goals. Its design goal was to be 100 times faster than its immediate predecessor, which was the 704. So if you think it's hard enough for us to get a machine which is 5 times faster than the non-pipeline RISC implementation, consider what their problem was, trying to get a machine to run 100 times faster. Part of the reason why it wasn't a commercial success was that it didn't work, and they didn't get 100 times faster. And to be fair, they only expected an increase of about 2 to 1 from the pipeline features of the machine. And the other performance increases came about, or were supposed to come about, for lots of other reasons, including the fact that they were radically changing the technology that they were using to implement it. The 704 was a tube machine, and the 7030 was going to be the first fully transistorized machine. No integrated circuits, of course, then, but transistors. So it's fascinating to look over this. I'll pass this around. I stuck a piece of paper in the section of the book where they begin to talk about their pipeline, and basically it was a 4-stage pipeline. But there are other sections of the book which are fascinating if archaic, like there's a long chapter discussing the issue of what number base this machine should use, whether it should be a decimal machine or a binary machine. And that tends not to be a question which people much debate anymore. In case you pass this around, and you're welcome to look at it. So last time we were talking about data pipeline hazards, and in particular we were looking at read after write pipeline hazards. And the basic problem is that if we follow the pipeline as originally designed, then the results of a ALU operation like this add, whose result goes into R1, doesn't get into the register file until the end of the write-back stage. Yet subsequent instructions that want to use it have to read that register back in the ID phase. So we've got at least 3 instructions that are potential problems that want to use the results of the add instruction and won't get the right result if we do the normal operation. Well, how can we fix it? One way to fix it is just to stall. We talked last time about several different techniques for stalling the pipeline in case things aren't ready. So we could, in fact, handle this problem by stalling. Anytime an instruction uses the result of a previous instruction 1, 2, or 3 instructions back, just insert a bubble into the machine, wait until the instruction producing the result has gotten past the write-back stage, and then let those previous instructions continue. The advantage of this is that it's cheap. It's an easy thing to do, because all you need is a little bit of compare logic that says, is there this conflict? And then insert no-ops into the pipeline in the appropriate stage to cause bubbles to be inserted. The problem with this, obviously, is that it would increase the cycles per instruction by much too much, because the most common kind of ALU operations are the ones where you compute a result and then immediately use that result in a subsequent instruction. So although one could build a machine that does this, it would occur much too frequently. Now there is, in fact, a much better technique for doing this, which is called forwarding or bypassing, and it comes about by recognizing that, in fact, we don't really need to wait until the result of the ALU operation is written 2 cycles later back into the register file before reading it. And let's take a look at how that works. With the same sequence of instructions we had before, although the result of the add, the result going into register 1, doesn't get officially written into the register file until the end of the write-back stage, in fact, those results are produced at the end of the execute stage. They're coming out of the ALU in cycle 3. They're needed by the next instruction, not necessarily at the beginning of the ID phase where it's normally fetched from the register set, but the first time they're actually used is at the beginning of its ALU cycle. So in fact, if we could manage to arrange for the output of the ALU in cycle 3 to get circulated back or short-circuited back into the beginning of the ALU for cycle 4, then we've solved this race problem, or this data hazard. Similarly, for the following instruction, it needs it again at the beginning of its execute phase. The result, again, was ready at the end of the execute phase at cycle 3, and somehow if we could get it from this end of execute phase to that end of execute phase, then we've solved the problem. Now notice you can't quite do this, because this is in fact moving forward in time. Time is moving horizontally in our diagram, and you can't forward results from one cycle in time to another cycle in time unless you've saved them. So in fact, you can think of this as happening in two steps. One is that the result of the ALU in this instruction gets forwarded on to the end of the next cycle, which in this case is the end of the mem cycle. And then if some other instruction at a different phase needs it, this is happening at the same time, you can forward the results from this instruction to this instruction. In fact, this progression is happening anyway, because the result of this ALU has to be making its way down the pipeline to eventually get into the write-back stage. So it's just a matter of snagging it at the right time in order to forward it to an instruction that needs it. So we can solve the problem for the subtract instruction, and we can solve the problem for the OR instruction by doing this kind of forwarding. In theory, we could do the same thing for the write-back. Rather than doing that, one of the things we can do is sort of finesse this. Instead of waiting for the end of the write-back cycle and forwarding to the beginning of the execute cycle, we're going to take another approach, which is basically to say that our register file is more complicated. Notice that what's happening here is that we're doing a write-back of register 1 into the register file, and during the same cycle, we're doing a read of register 1 into the register file. Well, I'm just going to wave my hands and say that that will work okay, that based on the design of our register file, if you write a register within a cycle, let's say that it happens in the first half of the cycle, then if you try to read that register, that same register, during the same cycle, let's say that happens at the second part of the cycle, that you'll get the right result. Now really what's going on in here is the same kind of forwarding that I've described for the other cases and that we'll see on the flow chart, but it's happening internal to the register file because we haven't exposed the details of the register file. That all make sense? Okay, so let's take a look at what changes we need to make to our previous pipeline diagram in order to get all of this forwarding to work correctly. I don't know if you can see the difference in color here, but the lightly shaded lines, the gray lines, are the ones that were added to show where the forwarding paths are. So we said that the input to the ALU, which used to come from the register file through these pipeline latch registers, now needs to have different sources. So we add two multiplexers in front of each of the inputs to the ALU. One of their sources, as before, is the register file. And in fact, these multiplexers were here because each ALU input before had two different places to come from, but now it has 4 different places to come from. For normal ALU operations that don't require forwarding, they can still get their results from the registers that latched, the pipeline registers that latched the register file output. But in the case where the previous instruction was the one executing in the ALU that produced the result, we need to have this bypass pass. Basically, the latched output from the ALU, which at the end of the ALU cycle gets put into this register, has to get fed back in the next cycle to be the input to the ALU, rather than taking the latched register data that came from here. So that takes care of the case where an instruction uses data that was computed in the ALU in the instruction before it. Similarly, we had a 2-instruction path where the instruction whose data had just gotten through the memory cycle and was latched in the memory write-back register here needed to go directly back into the ALU input. So this line was already here, hence it's black, but this gray line was added here to allow the result of the instruction at the end of the mem cycle to go back into the beginning of the ALU operation. Now notice that for all of these forwarding paths, there are two choices. There is a single register being written, but there are two registers being read, and the forwarding could happen for either or both of the registers that would normally have been supplied by the register file. So those two forwarding paths, plus the modification I described to the register file that allows a register being written to be provided to the same, during the same cycle as a register being read, essentially covers for all of the instruction-to-instruction read-after-write hazards that we saw on the previous slide. Now there's one additional path here which I've shown, which is a path from the end of the memory cycle back into the beginning of the memory cycle, which covers another kind of read-after-write hazard. Does anybody see what the hazard is that that has to fix for? Why might the input to the data memory have to come from the output of the data memory?
For stores?
Exactly. For a store, in which case?
In which case you use one of the registers to access as an indirect address?
You're talking about using a register as an address? That's not a problem, because the ALU operation computed the result of the displacement plus the register contents. If those register contents came from an instruction that was still in the pipeline, then that got forwarded back here with these paths.
If you do two loads in a row to the same register,
You're getting closer.
that'll, or maybe load in a store.
You got it. A load and a store. If you do a load, let's say we do a load word instruction into some register using some offset, and then the following instruction tries to store that same register into any other location. These two memory operations occur in adjacent cycles. So in fact, the output of the memory stage here has to be fed back into the input of the memory stage here. It's basically this register that has to be forwarded from the memory cycle back to the memory cycle. So in fact, that's what this other gray line here does. It takes, in one cycle, the data memory has read its result. At the end of that cycle, it gets latched into the write-back register. But for the next cycle, that same data needs to be written back into the memory. So instead of taking the data input to the data memory from this register, which came from this register, which came from the register file, two stages back, you need to provide it directly back into the data memory. Now what? Does that make clear? Make sense? Okay, let's look at what kind of logic you need to implement with forwarding. Basically, what are we doing? We're checking to see whether the destination... Yeah, question?
Yeah, well, what if you have a load word, no offload word? Is that last data path, or?
If you have a load word, no upload word. So the load word is in here, the no op is in here, and the load word is in here. Right, then you can use this other forwarding path for the data. Rather than feeding it into the data memory cycle, you can feed it back into the execute path. So we've already got that covered by one of the feedback paths. But in general, you've got to watch all of these combinations of instructions and possible feedbacks. And in particular, watch which combination of stages requires data to be forwarded from one to the other. And in fact, there usually wind up being a whole collection of comparisons that go on. And the comparisons are of the form, does this stage destination register match the source register for a previous stage? And if that's true, then we may have to change the conditions of these multiplexers in order to get the right data. And in fact, here's an example of those kinds of decisions. Let's say that execution has just finished an operation, and ID needs to read that value from one of the operands. So you need to do forwarding because the result is not going to be back in the register file in time for ID to read it. So you need to make a decision like this. And the book has a long table of all of the various cases, but this is just an example of one of them. Basically, IR4 was the register which contains the instruction which is currently has currently just exited the execution phase. So if you want to see what that instruction does or will do, you've got to look at the contents of the IR4 register. So if we look at IR4 and we determine whether or not that instruction is going to write a register by doing some decode that we can do right then, or we could have done it sometime before. So if it's an instruction that will write a register, and if the register number that it wants to write is the same as the register number which the instruction in the previous stage is trying to read, if it's the same as instruction register 3's previous instructions RS1 register number, then you have to change the multiplexer to select a different input rather than the register file. The same thing has to be done if it's reading the other register number. Remember, there's one destination being written, but in the instruction in the previous stage, there are two source registers that may be providing the result, and either or both of them may require forwarding. So you do two comparisons. One is, does this instruction write a register, and is the register that it's writing the same as a register that the previous instruction is reading? And if so, you change the direction of the multiplexer to use the forwarding path rather than the normal ALU path. Now, it could in fact happen that there are multiple places for the data to be coming. You may have two instructions in a row in the pipeline, both of which write register 1, and then the instruction just after that reads register 1. Well, what's going to happen in the pipeline diagram is, let's say that the instruction in X and the instruction in mem are both writing register 1, and you're about to move them to the next cycle. The instruction behind it is using register 1. Two of those comparisons will go off. Both of those comparisons that say the destination of this instruction and the destination of this instruction is a register that the instruction coming out of ID needs to use as a source operand. What do you do in that case? Which one do you take? Does it matter? Anybody?
Well, it's in the notes, but you use the one that's the closest in time, because that's, if you did it sequentially, that would be the one that would be in the register.
Right. You've got to maintain the semantics of the program, so that you've got to be careful not to use a register even though it's stored if a later register is going to update that result. So you've got to take the one closest in time. I guess I should read forward in my notes too, so that I don't ask questions whose answers are already down there. Any question about that? Let's look at the number of different forwarding paths, in fact, that we might need to try to get an idea of how many different comparisons we're actually going to have to implement in this machine. Well, the first one that we looked at was the end of execution forwarding to the beginning of execution. And in fact, there are two source registers there. So there's one comparison, and there are two different places you have to make it to compare the two different source operands. The memory stage has to feed back to the execute stage for instructions that are two apart. And again, there are two different comparisons there for two source registers that have to be compared. And then there's the memory stage going to the memory stage. And that was for the case of a load followed by a store. And in that case, there's only one comparison, because there aren't two source registers. There's only a single source register and a single destination register. So basically, there are about 5 sets of compares that need to be done. Now, it's not quite this simple, because remember, there are two different source registers, and in fact, there's only one destination register. But one destination register can appear in two different places in the instruction. And these comparisons, after all, are just comparing bits in the instruction field of one instruction to other bits in the instruction field of another instruction someplace else in the pipeline. How do you know where to look in the destination register? Well, where to look in the instruction to find out which is the destination register? Well, there are basically two ways of doing it. One is that you can essentially do multiple comparisons. You might consider doing another two comparisons for the two destination locations. And the only thing that you move along from one stage to the other in the pipeline is the raw instruction. After all, that's got all the information you need to determine where the destination register number is. Well, you might as well just carry that information on and compute each time where the destination is. An alternative is to do some pre-computation early in the pipe. You could, for example, decide to, in the ID phase, to pre-compute the number of a register which is going to be written and pass that along in the pipeline as well. Remember, we talked about there being chains in the pipeline for the program counter as it moves from stage to stage, and a chain for the instruction register as it moves from stage to stage. You could also decide to create additional information, like the destination register number, early on in the pipeline, and then pass that along as well, to reduce, as in this case, the number of comparators or the number of decisions that you have to make in subsequent stages of the pipe. And in fact, the programming assignment that you're going to be working on is to take a machine like DLX or a MIPS Lite machine, which is not pipelined, and to make it pipelined, create these chains of data that flow from one stage to another, and then to implement bypassing to get the read after write hazards solved. And one of the things you might want to do is, in fact, create one of these destination chains to remember the register number, which is the target register for any particular instruction. The other thing I should point out with respect to the programming assignment, by the way, is that we're handing it out now, but it's not due until after the midterm. However, if you wait until after the midterm to start it, you've basically got a week. And although one could do it in a week, it's not advisable. It's not a very difficult programming assignment if you do it right. If it begins to be extremely complicated and you think you're winding up writing 1,000 lines of code, then you're doing it wrong, in which case talk to one of the DAs. But in either case, it's better if you start it before the midterm rather than waiting until after the midterm. Just a word of advice.
One other comment about that?
Yeah.
And that is that if you get started on this programming project before the midterm, you'll find it may come in handy as you're going through sort of your midterm exam.
Another good inducement to start the programming assignment early. Any other questions on hazards and data forwarding? You might think, in fact, that we're done, that we've solved all of the problems, but in fact we haven't. There is one data hazard left, which is basically unsolvable. It is the case where a load instruction is followed by an ALU operation that uses the result of the load. Now, we just saw that if it's a load followed by a store, we're in good shape, because the store gets its data or needs its data only in the following mem cycle, so we can forward from mem to mem. In the case of a load followed by an ALU operation, well, in theory, we needed the result of the load in the ID phase, but we're willing to punt that. We understand now how we can forward to the beginning of the ALU without having to forward to the decode stage. But that still doesn't help, because the data isn't available until the end of mem, and we absolutely need to have it at the beginning of the execute cycle to get it into the ALU. And there's basically no way to do that unless you have some magic that allows you to go backwards in time. There's a comment here about tachyons. Tachyons are particles that go faster than the speed of light. And if you had a tachyon, in fact, you can invent a universe where cause and effect are reversed. So if you can do that, then we can solve this data pipeline hazard. But if you can't, then we've got a fundamental problem. What was that? Extra credit, right. You will ace the midterm if you invent a tachyon that can produce, that can solve this data problem. So there are basically two things we can do. One is you can stall. You can require that every load instruction be followed by a stall cycle, or every load followed by an ALU operation be followed by a stall cycle. And in fact, machines have done that. Or you could just decide that this kind of code is illegal, and that if you write this load instruction followed by an ALU operation that uses its result, you'll get the wrong answer. And that requires the least amount of hardware because you haven't fixed the problem. All you've done is document it. And in fact, that's what was done in the original MIPS 2000 machine. Basically, it's called a load delay, and you're allowed to follow a load by any instruction you like, and it won't stall. But if you follow that by an instruction that uses the register being loaded by the load, you get the wrong result. Actually, it's not just as bad as getting the wrong result. It's worse than that. You sometimes get the wrong result. Because consider what would happen if the machine took an interrupt between this load and the subtract instruction that used it. We haven't talked about interrupts, but you can imagine that what that really does is insert a few thousand instructions in between these two, and by the time the interrupt is done, the load has certainly had its time to store the result in register 1, and it works correctly. So whether or not that instruction sequence works depends on whether you're lucky or unlucky enough to get an interrupt between those two instructions. Makes a very unreliable machine, unless your compiler or assembler even is willing to enforce this dictum by inserting a no-op if you try to use that sequence. Well, in fact, the other approach, if you want to make a safe machine, the one that you can't write bad code for, is to stall. And in fact, you can recognize with the same kind of comparator logic that we did for forwarding that the destination register of this load is the source register of a subsequent ALU operation, and you could decide to insert a bubble into the pipeline. And we saw some examples last time, at least in theory, of inserting bubbles into pipelines, and this is a case where, in fact, we could use it in a practical way. I've shown the inserted bubble just a little bit differently in this diagram than I did before by having a separate line that represents a stalled instruction, but really the same thing is happening that happened before. The subtract instruction gets into instruction fetch, it gets into instruction decode, and it's at the end of instruction decode that you recognize that there's this conflict, that it wanted to use the register that mem was writing. So at that point, basically, you insert a bubble into the pipeline. You create a no-op, which delays the subtract instruction. Another way of saying it is that the instruction decode part of the subtract gets done twice. It gets done once in cycle 3 and once in cycle 4. Once you've done that, then you can use our normal forwarding trick and forward the output of the memory read at the end of cycle 4 to the input of the ALU in the execute cycle of cycle 5. And from then on, instruction execution continues in sequence. So that makes a safer machine. It's not, in general, a bad thing to do. The original MIPS processor, in fact, MIPS didn't stand for million instructions per second. It stood for microprocessor without interlocked pipelining stages. And they sort of had as their mantra that they would not interlock the pipeline for any of these kinds of operations. So they didn't stall for a load interlock. Subsequent versions of the MIPS processor, in fact, do have interlocks. Now, given a machine that does that, where you can't have a load followed by a subsequent operation that uses it, what can we do in software to make it less of a problem? Well, one thing we can do is to try to fill up that load delay slot, with something that doesn't cause us any problem. If we're given code that originally looks like this, where there's a subtract instruction doing something or other, and then sort of the normal sequence, a load followed by an instruction that uses the result of that load, this would either operate incorrectly if there are no interlocks, or it would operate correctly and cause a one-cycle pipeline delay if there are interlocks. But we can do better. In fact, this subtract instruction, we notice, is independent of the load instruction, so we can schedule it following the load instruction. So we begin the load, we do the subtract. None of the registers that the load needs, like R2, depends on the result of the subtract instruction. So we can do this interchange safely without changing the semantics of the program and avoid the interlock and make this a useful instruction. This can be a big win. And in fact, we'll see in a second some of the numbers that say that we can really get a win of 30% because this sequence is so common of loading a register and then using the result of that register. But there are limitations to how much this can buy. One is that in the presence of branches, doing this kind of rearrangement is much more difficult. And we've got lots of branches. 15% or so of our instructions are branches, so there are only sequences in basic blocks without branches in the middle of 5 to 7 instructions that we get to play around with to do this kind of rearrangement. The other is that some sequences that look like it might be possible to interchange or to rearrange turn out to be a little bit dangerous, and some of those have to do with pointers. Let's say that we had the following sequence of store instruction. So we're storing register 1 into 0 of register 4, say, followed by a load instruction, which is going to be loading another register, register 2 from 0 of register 5, say, and then some other instruction following this which uses register 2. So we've got the conflict here. We've got the load delay, and we want to reschedule this code in order to be able to put a one-cycle delay between the load and the add. Well, looks from cursory examination that this store is a good candidate. We could just take this store instruction and insert it into here. After all, it obeys the rule I said before. None of the operands of the load are changed by that store instruction. But this is a dangerous thing to do. Why is that? Anybody see why this might not work?
Aliasing on R4 and R5.
I'm sorry?
Aliasing on R4 and R5.
Exactly right. I mean, the problem in general is called aliasing, and the problem is it's hard to tell when you're using pointers whether or not those pointers point to the same thing. Had I rewritten this code sequence like this, had I said store register 1 into 0 of register 4, and then load into register 2, 0 of register 4, you would have seen immediately that it would be dangerous to interchange them because this store is storing a result that this load needs to reload. Well, if at execution time it just happens that register 4 and register 5 have the same value, they're both pointers in C that are pointing to the same thing, then rearranging the store and load instruction is going to make your program not work. So compilers have to be very careful in doing this kind of operation. Now, obviously, had you written the instruction sequence like this, the compiler could be clever and notice that register 1 being stored here is register 2 being loaded here. But after all, this looks like pretty dumb code. Here, the code doesn't look so dumb, and the compiler has to be smart enough to recognize that it can't do this rearrangement. But even with that problem, it turns out that load scheduling is a big win. And if you look at some numbers from DLX, this shows the percentage of loads that cause pipeline stall. And on some of these examples, it can be high as 40 to 60%. If you haven't done any scheduling, if you haven't done any rearranging. If you do a rearranging, you cut it down to, in most cases, less than half. So in the case of tech, it goes down from 60% stalls, or no ops that you would have to insert, down to 20 or 25%. So load scheduling is a big win, even if you can't solve the problem for memory aliasing. Yeah.
If the hardware can do a store word after a load word of the same register, why did the R2000 decide to make that illegal also?
If it can do store word followed by a load word?
A load word
followed by a store word?
Right.
I'm not sure. And I'm not sure whether that is a case which is illegal in the original MIPS 2000. It may be that they just took the simple approach that any load followed by any instruction that uses that register causes a load delay, is disallowed. Now, in fact, it would be interesting to get an original MIPS 2000 and try it and see if that sequence works or not. I don't know the answer to that. Try to find out. Okay, so we have fixed, at least I claim, all of the data hazards. We only had after all read after write hazards, and we've gone through all the cases, and we only have one thing left, which is branches are broken. When last we looked, we had a problem because the new PC that we needed as a result of a branch, let's say that this was a branch instruction, is not available until the end of the mem cycle. And the instruction that next we want to execute got fetched back in cycle 2. So if we want to solve this in sort of the mindless fashion which we understand works, which is to say stall, then we have to stall the subsequent instruction from when it was to have been fetched, which is cycle 2, to after the mem stage when our new program counter is known, resulting in a stall of 3 cycles. Well, we can do that, and in fact it works, but it's a lousy thing to do for performance because branches occur every 5 or 7 instructions. If that represents 15% and the branch penalty is 3 cycles, then our penalty for branches is 0.45, which means that we've increased the CPI of our machine to 1.45. Just the effect of doing branch delays for 3 cycles has really hurt our performance. We've gone from a 5 times throughput improvement in the pipeline that we were hoping for to something like 2.5 times throughput improvement. So obviously we need to work harder to make that better. And there are basically 2 things we need to do. One is that we need to determine the branch condition as early as possible. And the other is that we need to compute the target address as early as possible. Now these things can be produced at different cycles of the machine. Right now we've got them produced so that the later of the 2 comes out at the end of mem cycle. Question is, can we do better than that and reduce the number of stalls? Well, in fact we can. And part of the reason why we can is we carefully designed the instruction set of the DLX machine so that branches are easy to do. Notice that for DLX, the branch is a very simple test. It only checks for equal or not equal comparison of a register to 0. Well, right now we're going through the entire complicated ALU back in the execute stage to do that. We don't have to do that. In fact, we can use a 32-bit NOR or OR gate to check for whether or not that register is 0 and create a new piece of hardware to do this special purpose test rather than wait until the execute cycle to do that test in the ALU. So that gets us a branch condition which we'll see in fact can be moved into the ID phase rather than the execute phase. Now what about the branch target? Well, the branch target right now gets computed in the ALU by adding PC plus 4 to some sign extended value which was pulled out of the instruction field. Again, we're using the general purpose adder and we're using it late in the cycle because that's where we need the adder for other operations. Why don't we build a special purpose adder, which for branches at least only has to be a 16-bit adder plus carry propagate to the rest of the 32 bits, and stick this special purpose adder for the branch target as early in the pipeline as we can. Well, in fact, we can do that, and we can put that into the ID stage as well. We can also do that for the jump target. The jump target is a little bit more complicated because as it's defined in DLX, it's still PC relative, but in here we need to add a 26-bit immediate field to the PC and do carry propagation. This takes a little bit longer. Notice that we're trying to squeeze all of this stuff into the ID stage. The ID stage is already doing a lot of work, including fetching registers and so forth. If you're adding things into the serial path that take a long time, like a 26-bit adder, you may be stretching the entire cycle time of the machine in order to get stuff into the ID cycle. One of the decisions they made in the RailMIPS CPU, in order, in part, not to have that problem, is to allow jump target addresses to be computed without doing any addition at all. And in the real MIP CPU, the target address is computed by taking an offset part from the immediate field of the instruction, concatenating rather than adding certain of the high order bits of the program counter, and then in fact shifting it left 2 bits because instructions are always on a 4-byte boundary. And the result of that definition of the instruction set is that it requires no adder at all. So in fact, you don't even need a 16-bit adder to do a jump target in the real MIPS. Well, we're going to make the assumption that for us, we have enough time to do a 26-bit addition plus carry propagate to 32 bits for jump targets. And we're going to move all of this logic to the ID stage, even though it costs us additional hardware, and may, depending on the details of the propagation delays through this stuff that we're adding, cause us to increase the cycle time. But because branches are so common, this is going to be a win. It's going to be a useful thing to do. So what's the hardware we have to add? Well, we're moving into the ID stage, this new special purpose adder, which adds the result of sign extending an immediate field in the instruction to the value which is currently latched in PC2, which is PC plus 4 for that instruction. And then we have to decide in the ID field whether or not to use that incremented value or PC plus 4 in the case of no branch. Well, in order to make that decision, we have to test a register. So we put, again, into the ID stage, comparison to 0, which is, again, just a big 32-wide NOR gate or OR gate. And it, in normal cases, takes its input from the register of the branch instruction, which is currently executing in the ID phase. Well, remember, just as before, we had the problem that that register may be being written by immediately preceding instructions that are executing further down in the pipe and haven't yet written their results back to the register file. So we have to have a similar kind of forwarding or bypass mechanism to choose the register to test from either the register file or the output of the ALU in the execute section, or the output of the memory multiplexer in the MEM stage. And in a sense, we're duplicating the kind of forwarding logic we had over here at the end of the ID phase in order to get the test to be done at the right time. All see that? Any questions about that? Now notice, in fact, that there are, in general, 2 different ways to do this kind of forwarding. I chose, mostly because the book does it, and I didn't want to confuse you, to do forwarding from the beginning of a cycle, like our old forwarding path went from the beginning of the MEM cycle back to the beginning of the ALU cycle. In fact, that's not the only way to do it. You can also choose to do forwarding from the end of a cycle to the end of a cycle. So I could instead have chosen to put the multiplexers on the other side of these pipeline latch registers, in which case I would have forwarded from the output of the ALU to the end of the ID cycle. If I had done that, in fact, then I wouldn't have to be duplicating this multiplexer. For the case of this so-called early control point, where we want the branch decisions to be made in ID, we really need to have that decision done at the end of the ID phase. In the case of the other forwarding paths, it's not as critical. We can choose to forward from end of cycle to end of cycle, or from beginning of cycle to beginning of cycle. I hope that wasn't too subtle a point.
Does this diagram show the any jump concatenation?
I'm sorry?
Does this show any jump concatenation?
Jump concatenation. You mean the computation of the target address by concatenating parts? No, this is the DLX machine, where the target address is always being done by adding to the program counter something that's coming out of the immediate field. Now notice one of the details that I sort of fuzzed over here was how this sign extension is really done. That a sign extension might be, in the case of a branch, sign extension of a 16-bit value. In the case of a jump, that might be a sign extension of a 26-bit value. And the decision about that has to be made depending on what instruction is currently in the ID phase. So there's a there's more input to this sign extender than just the immediate field. It also has to look at opcode bits to decide what kind of sign extension needs to be done. But in fact, that's a problem we had before as well. The sign extender always had to do that. There were different kinds of sign extensions. Now, how well have we done? Have we removed the stall or branch penalty? The answer is no, because there still is one cycle delay. While we're doing this computation here, the previous instruction, which we would like, if at all possible, to be the target of the branch when the branch goes, is not the target of the branch, and we still are one cycle late. So in fact, we either have to stall for one cycle following a branch, or we have to figure out some other way to use that cycle. But basically, there's no way we can make the branch delay be 0 in this kind of a structure. We always have at least one cycle penalty. Well, let's look at some statistics for branches so we can see how they're used, and maybe from that we can get some ideas for how we can minimize even that one cycle penalty. These are some statistics from 3 different instruction set architectures, the VAX, the 8086, and the DLX, that try to compute how many conditional branches there are. One of the things that we see right away is that the VAX has a lot more, on a percentage basis, jump or branch instructions than the RISC-like processors. And that makes sense, because its instructions do more. And you can get a basic block, a sequence of instructions between jumps, to do a particular piece of operation in fewer instructions on a VAX-like instruction set than you can on a DLX-like instruction set. So that makes sense. But even for DLX, the sum of conditional and unconditional branches is something like 13 or 14%. And most of them, unfortunately, are conditional branches. Unfortunately, because those are harder for us to deal with. We can't tell by looking at the opcode whether or not they're going to go or not. On the whole, taking branches and jumps as combined, branches, remember, are conditional and jumps are unconditional, about 65% of them go somewhere. 100% of the jumps, obviously. If you look only at branches, then you notice a very interesting dichotomy that of the backward branches, 90% of them, in fact, execute. These are dynamic numbers based on counting the number of times that branches in the program actually branched their target location. 90% of the ones whose target is backwards to a smaller program counter address branch. Now, that's pretty obvious when you think about it, because those are all loops. All the loops have backward branches. Sometimes you have a backward branch which is not a loop. Mostly for well-written programs, those tend to be procedure returns rather than go-tos. So it's not surprising that this is true. Forward branches are not as easy to predict. These are probably mostly if-then-else kinds of constructions. And I guess 40% forward branches says what? It says that the then clause is executed 60% of the time compared to the else clause. So we can't get much mileage, however, out of predicting this, but we could perhaps get mileage out of predicting that backwards branches are going to go, because that's almost always the case. Let's look at some ways of dealing with these branch penalties. Well, one thing we can do, which turns out to be the easiest thing to do, is just to predict that the branch won't be taken. That whatever the instruction is that follows the branch is going to get executed. So that one cycle instruction we should execute. We should continue to execute. And this is easy to implement, because if the branch is not taken, then we just continue. There's no stall, there's no delay, there's no no-op. We just continue executing. If it is, then if the branch is taken, then we have to take that instruction, which is partially executed, hasn't done any damage yet, and turn it into a no-op. So basically we just jam, I guess that instruction is what? Now moving into the execute phase, we can take that instruction and change its instruction register to all zeros and turn it into a no-op. So we've got a sort of a conditional no-op here. Well, this helps a little bit, but it bets the wrong direction, because especially for loops, 90% of the instructions are going back. Betting that the branch is not going to be taken is a bad thing to do. Well, okay, let's take the other approach then. Let's let's guess that the branch is going to be taken and try to make that our high probability case. Well, on DLX, that's not going to help us very much. The only time that that's a useful thing to do is if the target is, excuse me, if the target address of the branch is known before the branch condition, so that you don't know whether it's going to be taken yet or not, but you know that if it's going to be taken, you know where that instruction is. So if your model is that branches are most often taken, and you know where that instruction is, but you don't know yet whether it really is going to be taken, still it's your better bet to start fetching that instruction rather than fetching in line. Again, for DLX it doesn't help because we know the target address and the branch condition at the same time. For machines like VAXs or like even some of the RISC machines that have condition codes where the branch condition is not known until end of X or maybe even end of mem if condition codes are set on memory loads, then this in fact might be a useful thing to do. Start fetching the target instructions rather than follow the fall-through instructions. Yeah.
Is it DLX that makes it, or is it makes it so we don't want to fetch? I mean, if you look at the machine model that you had on the previous page, it seems like the conditional check is sort of the last thing sequentially you're going to get.
Right.
You know, it's sort of like has the longest delay before the adder's output should be ready before the condition is. Now,
yeah, the adder should be out somewhat earlier.
So it's sort of like, it seems to me we made a choice to include those things in the same phase, but it's not necessarily a quality of DLX. I mean,
well, it's a combination of things. One is that we get a chance to do it here because the condition test is only on the register. If the condition test was on the output of the ALU because the condition code had to be set, or it was the output of mem stage because loads changed the condition code, we wouldn't have the opportunity to do that. But what you are pointing out, I think, is that, in fact, even testing a register may wind up taking too much time, and we might want to push that into the execute phase. Was that the question you were asking?
Yeah, because when you're testing a register, you might actually be forwarding the data from a later stage. In that case, it might be kind of late.
That's right. And in fact, it's likely that by adding all of this logic to the ID phase, we have expanded the amount of time we have to take, which is slowing down all stages of the pipeline. And then this is a great midterm question, you have to make a decision about whether or not it's better to take an extra cycle hit on the branches and keep the pipeline cycle times short, or don't take the extra hit on the branches and make the pipeline cycle time longer. It's one of these standard performance improvement trade-offs. So there are two things you could do. You could bet that the branch won't be taken, or you could bet the branch will be taken. If you really want to be fancy, and we'll talk about some machines later on that do this kind of thing, you can take both bets. And if you've got enough hardware in your machine, you could start fetching down both paths, both of the target path and the fall-through path. And based on what the eventual outcome is, you can decide to throw away one path or the other. One of the earliest machines that did this was the 36091. And the 360, remember, is an instruction set architecture that has condition codes. Computing the target address can be done very early in the cycle. Computing the condition code is done late in the cycle. So in fact, fetching down both paths as quickly as possible and doing decodes and as much execution as you can, and then throwing away one or the other when you eventually get the condition code is a great thing to do. And 36091 did it.
Question.
Yeah.
Suppose you have stored a memory address, then how do you throw it away?
You don't. You can't. And in fact, one of the things you've got to be very careful about when going down both paths is that either you delay making changes that you would have to undo, or you have to undo changes. It's not just storing memory addresses. What if you change registers? Yeah. Anything, this is kind of speculative execution. Anything that you're executing where you're not absolutely sure that you're going to want to execute it, you've either got to save a way to undo it, or you've got to delay the effect of changes. And that's what makes that kind of thing very complicated.
Question?
Yeah.
What kind of advantage might that give for a non-pipelined architecture? I guess none.
For a non-pipelined architecture?
Yeah, because you said it was first used in the 360. What 360?
Yeah, it was first used in the 36091, which was definitely a pipelined architecture. 360. The 91 came out in, 66 or 67, something like that. So it was way beyond the stage of the computer whose book is going around, which was in the late 50s, which was already a pipeline machine. Pipelining is not new. Although in some sense it's had a renaissance with all of the RISC processors, which can take advantage of pipelining much more than the complicated instruction sets. Still, pipelining has been around for forever in the computer business, which is about 25 years. Now, what is new is the freedom that people now have to decide that if they can't solve this problem, then they're going to legislate it away. And one of the ways of legislating it away in a RISC-like architecture is to change the definition of the way branches work. And we can decide, because we can't manage to deal with the instruction that follows a branch, that that instruction is always going to execute, whether or not the branch goes to its location. And it's up to the compiler to find some instruction to put into this so-called branch delay slot that will do something useful, whether or not the branch instruction eventually branches. And we'll look at different cases where that's possible. One of the problems with making this kind of change, again, this is an interaction between the implementation of a processor and the design of instruction set of the kind we talked about before, that is a little bit dangerous to do because, well, let's say that the current implementation with the pipeline we're talking about has one branch delay slot. And we tell the compiler, okay, we're going to execute that instruction regardless of what the branch does. That's great. What if the next implementation for that same instruction set, because it's a different pipeline and cycle times are different and technology is different, well, now we need two branch delays. We can't do it with just one branch delay. What do you do about existing programs? You change the design of the instruction set and tell the compiler that now you've got to put two instructions, or find two instructions to stick after the branch to do something useful. Number one, that's harder to do. We'll see, it's hard enough to find one instruction to put there. It's a lot harder to find two instructions to put there. The other is that it leads to all sorts of complications with respect to compatibility with the current version of the machine and the old version of the machine. So it's always kind of an aesthetic challenge to find the modifications to make to these instruction sets that will work well for many implementations but aren't confining or aren't too specific for particular implementations. Notice that in a lot of ways this is worse than the load delay. Right? We had a load delay where you might, if you're not going to stall, have to tell the compiler that it has to put a no-op in after the load. Well, if you do a new implementation that removes the requirement to do that, your programs will still execute because you've got a no-op in there and you didn't need to put one in there, but it doesn't do any harm. But if you schedule something into a branch delay slot and the next version of the processor says, well, there is no branch delay slot, that instruction is only going to get executed when the branch doesn't branch, your program now doesn't work. So this is even a worse case of mixing the instruction set architecture and implementation than the branch delay slot because it has more implications for program on the programming itself. Well, be that as it may, let's take a look at the case of a single branch delay slot and figure out when it can be useful. Well, there basically are three places you can pull instructions from. Let's say we've got a conditional branch here and we've got this delay slot that we've got to stick something into that will get executed whether or not the branch goes. Well, we could always do a no-op, but that's a waste of time. We could sometimes take the instruction or an instruction from before the branch and move it around the branch to the branch. If we can do that, then it's always a win because we had to have executed that instruction anyway. We needed to execute that instruction. As long as the branch doesn't depend on that instruction, on that add, then it's a safe thing to do. So if you can find an instruction that the branch doesn't depend on and move it from before the branch to after the branch, then it's a great win. You've essentially erased the delay. It's hard to do because, as you might imagine, like with the load followed by ALU operation, there are lots of cases where you have an ALU operation followed by a branch that tests the result of that ALU operation. Well, if you can't do that, then another possibility is to pull the first instruction from the target. Let's say this branch is going to branch to a subtract instruction down here. You might consider taking the subtract instruction and moving it up into the delay slot. Well, you can do that only if it's okay to execute that instruction in the case when the branch is not taken. In this case, for example, if there were an instruction down here that used the result of register 4, you couldn't do that, because the subtract instruction in the case where the branch wasn't taken changes register 4 to a value that it wouldn't have had if you didn't do that move. So it's only okay to do sometimes, as in the other case, and it only wins if the branch is taken. If the branch is taken, you got the execution of that instruction for free. If the branch is not taken, then you executed an instruction in that slot all right, but it was a useless instruction because you didn't need to do it. The complement of that is to fill in the delay slot with the first instruction that would be executed if the branch is not taken from the fall-through slot. And you need to do an equivalent kind of test. It has to be an instruction that's okay to execute if the branch is taken. And again, it only wins roughly half the time. It's only a useful thing to do if the branch is not taken, and that instruction would have been executed anyway. So the challenge you give to your compiler writer is, this is the best thing to do it if you can. These things are okay but not as good. Do it if you can, because it's certainly better than sticking a no-op in. And if you can't do anything, then you stick a no-op in. Well, yeah.
So if you put something in that slot and then you decide not to, that was a useless instruction,
right,
would you kill that instruction like right away on the next cycle?
The model here is that instruction doesn't get killed. That instruction gets executed always.
But what if it's writing something into memory?
Then you better not have put it there.
So
It's got to be an instruction that doesn't cause any bad side effects if it's coming from the wrong path. And that includes loading a register, like in this case register 4. You can't modify register 4 in the delay slot if register 4 gets used later, or if it's storing in memory.
But how much later is later? I mean,
basically any time later, any time in this basic block. I mean, you've got to convince yourself, and it's hard for the compiler to do, that register 4 doesn't matter at the end of this delay slot in order to be able to put this instruction there. Now, in fact, compilers can do that. They do what's called live dead analysis all the time to figure out whether the value of a register or a variable has any useful meaning at this point in time. And they do that by analyzing the entire flow control of a function. So the compilers that are smart optimizing compilers have this technology built in. It's really not that much of a stretch for them to do this analysis. The big question is how often, what percentage of the time does it work out? Can they find something to stick there? And in fact, that's the next slide. This shows for DLX-like machine and for several different benchmarks what percentage of the time the slot got filled with an instruction which wasn't a no-op. And those numbers look pretty good, in fact. It looks like more than half of the time you fill the slot with some instruction that would be legal to execute there. And then the next question is, of those instructions, how many of them are useful in the sense that they do something that you really need to do? Like in the case, excuse me, like in the case where we took the instruction from before the branch. And the answer is most of them. You only lose about 10% of those slots because that instruction was not a useful one to execute. So again, this technique of using compiler scheduling for filling in the delay slot is a big win.
Question?
Yeah.
What do you mean by not useful? Since we said that all the instructions that are in the delay slot must be correct, so they actually do something that is not wrong, and they are not knobs, so how can they not be useful?
Well, they're not useful because you didn't need to execute them. Their result wasn't used in the computation, right? You got it? They don't do any harm. They're not no-ops, but they're wasteful. You didn't need to execute them. Okay, let's look at these various strategies and see what effect on cycles per second we have. Well, we know that the effective cycles per instruction is going to be 1 for our pipeline machine with no other stalls, plus the percentage of branches that we execute times the average branch penalty. Well, we know that 14 of our instructions for DLX-like machine, 14% of our instructions are branches or jumps, and of those instructions, 65% of them go to the target. So let's look at these various strategies and see what resulting CPI we get. Our original proposal was to stall, and in that case, the penalty if the branch is taken or the penalty if the branch is not taken is 3 cycles, and 14% times 3 cycles is 0.42 plus 1 is 1.42, number we had before. Not great. Well, adding our additional hardware and moving both the branch target address computation and the branch condition computation into the ID reduced the branch penalty to 1 in both cases, taken or not taken. In that case, we're getting we're getting 14% of the instructions where branches are taken, and 14% of the instructions where branches are not taken. In both cases, it's a 1-cycle penalty. The result is a net 0.14 cycles penalty for the branches. So we've slowed down our machine by a much less amount by moving the branch into the ID. I'm sorry, you're right, 0.35. Thank you. Well, in DLX, as we pointed out, predicting that the branch is going to be taken is not going to help us, because even for predicting branch taken, the penalty for branch taken is still 1 cycle. We can't do any better than that. So we get, for DLX, although not for other machines, the same penalty. If we were to predict branch not taken, and then nullify the instruction if the branch is taken, then we get a 1-cycle penalty in the case of the branch goes, a 0-cycle penalty in the case where the branch is not taken, and we could get down to 9% overhead. In fact, we've chosen to insert a branch delay slot, and the numbers from the previous page of statistics show that about half the time the branch delay slot is useful. So about half the time for a branch taken we take a 1-cycle penalty, about half the time for a branch not taken we get a 1-cycle penalty. In fact, we do even better than hardware that predicts not taken. We only get about a 7% cycle degradation. So we've gone down from an effective CPI of 1.42 to 1.07, which is very good. It's in fact a lot better than you can do in more complex instruction sets. And it's a lot better than you can do in other pipelined implementations of RISC instruction sets where the pipeline is deeper and you have to pay more than a single cycle penalty. Any questions? Next time we'll start talking about some other pipelines for other instruction sets and other implementations.